Ever wonder how your favorite app just knows? Like it has this sixth sense for what you're going to ask for next. It's like it has a photographic memory for what you need right now, but it's also smart enough to forget everything else in the blink of an eye. Well, that's not magic. It's one of the most elegant data structures out there, the LRU cache. And today, we're going to pull back the curtain and see exactly how it works. You know that feeling, right? You're scrolling through photos, loading a web page, whatever. You tap, and boom, the data is just there. It feels totally effortless, but behind the scenes, oh, there's some seriously clever engineering going on. And a lot of the time, the secret weapon is a clever little thing called a cache. Think of it like a small, super fast pocket of memory that's always trying to guess what you'll need next. But here's the catch, and it's a big one. Its space is really limited. So it has to make some tough decisions, what stays and what gets the boot. This whole problem really boils down to a classic trade-off in computing. See, we've got tons and tons of slow storage for all our stuff, but only a tiny, tiny amount of ridiculously fast memory to actually work with. So the whole game is about being incredibly smart with how you use that tiny, precious fast lane. So let's just define it. What is a cache? Well, it's basically just a storage spot with a fixed size, that's the bounded capacity part, that keeps a copy of the data you've just used. The goal is super simple. Have what you need ready and waiting in that fast lane so you don't have to make that long, slow trip back to main storage. Okay, so before we dive into the code and the data structures, the real nuts and bolts, let's build a super solid mental model first. Honestly, the best way to get your head around an LRU cache is with a really simple, everyday analogy. I want you to picture just two things. First, a classic old-school phone book, and second, a single file line of people. I know it sounds simple, but trust me, these two things are pretty much all we need to understand this whole concept. Okay, so check out how these two work together because they each have a very specific job. The phone book, that's all about speed. You need to find someone, you just look up their name, boom, you've got them instantly. The line of people, though, that's our timekeeper. It's basically a living record of who you talk to and when. The person at the very front is who you just talked to, and the person way at the back is who you talked to the longest time ago. So here's the rule. Let's say you look up Alice in the phone book. The second you find her, it doesn't matter where she was in the line, could be the middle, could be near the back, she immediately walks right up to the very front. Why? Simple. You just used her info. She is now the most recently used person. Right, but what happens when the line is totally full and a new person, let's call him David, shows up? There's no space. Well, the rule is simple. The person who's been languishing at the very back of the line for the longest time, our least recently used person, has to leave. That frees up a spot, and David can go right to the front. And that right there is the core logic of LRU in a nutshell. Okay, that analogy seems pretty straightforward, right? But how do we actually build this in code so that every single one of those actions, finding someone, moving them to the front, kicking someone out, happens like instantly? Well, this is where two classic data structures team up to do something really, really cool. So that super fast phone book we talked about, in the real world, that's a hash map. Its superpower is giving us what's called constant time or O1 lookups. Basically, you give it a key, like a person's name, and it gives you back their information almost instantly. It's like a magic index for our data. And what about our line of people? Well, that's a doubly linked list, and it's just brilliant for this. See, in a doubly linked list, every single item knows exactly what's in front of it and what's behind it. This means we can just grab an item from the middle and move it to the front, or chop an item off the back without having to reshuffle the entire line. And guess what? That's also a constant time, a one operation. And this right here, this is the holy grail, O1, constant average time. What does that actually mean? It means that it doesn't matter how big our cache gets. It could have 10 things in it or 10 million things. The time it takes to find something or add something stays pretty much the same. It doesn't slow down as it gets bigger. That is an incredibly powerful guarantee. So you see how they're the perfect team, right? The hash map is our speed demon. It answers one question instantly. Do we even have this thing? Meanwhile, the doubly linked list is our meticulous timekeeper. It answers the other crucial question. What's the order of use? One finds, the other orders. And together they give us that beautiful O of 1 performance we're looking for. All right, so we've got the theory down. We have our two key players. Now let's actually watch them in action during the most interesting moment for any cache, What happens when it's totally full and a new item tries to get in? Now, this is a super important point, so I want to make sure it sinks in. Anytime you access an item, it doesn't matter if you're just reading it or changing it, you have to update its position. It always moves to the front of the line, to the top of our recency stack. That one simple move is what makes this whole thing work. And this brings us to the eviction dance. Let's walk through it. Okay, so the cache is at capacity. Step 1, a new item shows up. Step 2, we don't wait, we immediately put it at the very head of our list, making it the new most recent. Step 3, we look all the way to the other end, to the tail of the list, to see who the least recent item is. And then steps 4 and 5 are just cleanup. We remove that poor item from the list, and then we remove its key from the hash map so we can't find it anymore. See? The two data structures working in perfect sync. Okay, so this is a really elegant, high-performance solution. It's a fun little computer science puzzle for sure. But so what? Why does this actually matter in the real world? Well, the answer is pretty amazing. It's basically running everywhere all around you right now. I mean, think about it. Your computer's operating system, the actual CPU chip in your machine, the giant databases that power pretty much every app you use, the web servers and CDNs that deliver you this content, they all use some form of LRU caching to speed things up. And yeah, because it's so fundamental and just clever, it's an absolute classic you'll see in coding interviews all the time. Now, to be fair, LRU isn't the only way to do this. There are other strategies. You've got FIFO, first in, first out, which just kicks out the oldest thing, period. Then there's LFU, least frequently used, which actually counts how many times you use something. But they all have trade-offs, right? LFU, for instance, can get stuck holding onto something that was super popular last week, but is totally irrelevant today. For a ton of common situations, LRU just hits that perfect sweet spot. It's simple and it's incredibly effective. So let's just boil it all down. What are the key things to remember? First, it's that magic combination, a hash map for speed and a doubly linked list for order. Together, they give us that awesome O1 average time for getting and putting things in. The golden rule you can't forget is you have to update recency every single time you access something. And finally, when the cache is full, it's the item at the very back of the line, the tail of the list that gets the boot. But you know, this whole system is built on one big idea, that the thing you used most recently is probably what you'll need again soon. And is that always true? I mean, what if one item gets used 1,000 times an hour every hour, but you just happen to access some other random thing for the very first time? Should that new thing jump to the front of the line? It kind of makes you think, right? In the big battle for that precious cache space, when does frequency become more important than recency?